instructions. I printed one for everyone because there's only one paper. So you can keep this. We are looking at reaction rates. So we're going to look at 3 things that can affect the reaction rate. And we're going to see how do these 3 things affect the reaction rate. So that's going to be part of your conclusion. I think that's the post-lab. That's what you're going to try to figure out. How does temperature affect the reaction rate? How does particle size affect the reaction rate? Yeah. Oh, and then concentration. How does concentration affect the reaction rate? Did I just okay. So this is our paper. This is the instructions. Okay, this next one. This one is an extra paper. If you think this will help you, you can use it. If this is confusing, don't use it. Okay, this is about the lab. And it kind of gives you a template to build your procedure. But if this is going to be not helpful, then don't use it. Okay, this is not required. This is just extra. Also, it has a points thing on it. Don't worry. This is someone else's worksheet that we're like using, but we're not getting points based on the 200 points box. So don't worry about that. Okay. So there are 3 reactions that we are going to look at. And on your paper, they're right here. Maybe I need one of those. Okay, and these papers kind of are similar, but they're not the same. So we'll use this one from Weber State. But the other paper also has this information. So when I'm looking at this, we have 3 reactions. We are going to react magnesium with hydrochloric acid. We've done that before. That's what we put in the balloon, when the balloon got big. So that's one, and we're going to do that in a well plate. Okay, so your procedure should include a well plate. I think that could be confusing for this lab is that we have all these different chemicals, and we can only use certain chemicals for each experiment. Does that make sense? So we have 2 acids. Don't mix the acids up. Does that make sense? Don't use hydrochloric acid with the sodium sulfite. Your experiment won't work. So make sure that you're clear in your procedure and you're watching the vials that you're using. So make sure that you use magnesium with hydrochloric acid. We're also going to use Alka-Seltzer with water. So how many of you have done that? We're going to put it in a canister. You have used the canister? Okay. So we're going to put one of these tablets. You're going to get a tablet, and you'll mix this with water and put it in here. Okay. Okay, and the last reaction is one where you're going to take an indicator. So this is our indicator. This is ethyl blue, I think. I don't have it written down. This is our indicator. I just labeled it with indicator. I don't know if you can see that. Okay, indicator. And then we're going to take sulfuric acid, 3 molar sulfuric acid, and 0.5 molar sodium sulfite. So that's the 3rd reaction. Okay, so I'm going to go through all of these. What you need to do is you need to figure out one of these. You're going to figure out the experiment, how the experiment is affected by temperature. One of them you need to decide to test particle size. And one of them you need to use to test concentration. Okay? Does that make sense? So let me write out. Let's see, what should we do? Let's demo them, and then we'll think about what we're doing. Okay, so the first one I'm going to demo is the magnesium ribbon. This is our well plate, magnesium ribbon with hydrochloric acid. Okay, and I'm going to check and make sure that I have the right acid. This is 3 molar hydrochloric acid. I'm going to put my safety glasses on. And then I'm going to get a piece of ribbon. Okay, so if I was testing particle size, what could I do to measure the particle size? Or not, like to test the particle size. Talk to your group. So this one, I could test particle size. So you're going to get a piece of magnesium. What could you do to the magnesium?
What is particle size?
Oh, particle size. So this is like when I'm melting butter, if I cut it up, it melts faster. So I could cut this up. Yeah, this one bends really easy. Did you guys measure this out? So you can just like bend it. So maybe I'm going to test, I'm going to do like a big piece. I don't know how much I'm supposed to give you. So maybe I will give you more than this. So maybe I'm going to do like, let's see. I don't want to test concentration and particle size at the same time. So I'm going to, as best as I can, get similar size pieces. This one, I'm going to test the whole piece. I'm just going to bend it so it fits. Okay. I'm going to put it in there. And this one, I'm going to say similar size as best as I could. I'm going to break it into tiny pieces. So this would be how I test particle size. Okay. What if I wanted to test the temperature? How temperature affects this reaction? So what could I do? Yes. Thank you for saying that. We wouldn't want to change 2 things at once. So if I want to use this one for changing temperature, I would only change the temperature. So there's a few different ways that I can change the temperature of my reaction. I could put the whole well plate in like on ice, and that could change my temperature. I could put this, so I will have ice. And there's like a whole bunch of different ways that you can do this. So you just need to, if you need something, let me know. So I'm going to bring ice. We will have hot water. This tap water gets almost to 40 degrees Celsius, so it gets quite warm. So you could change the temperature with the water. Okay. One way to do that would be to change the temperature of your reactant. So if I take my reactant and heat it in, if I put it in another beaker, so imagine, I'm going to take all these droppers out. I put some either ice water or hot water, just a little bit, and then I can put my reactant in there, and then this would heat up or cool down. And that could modulate the temperature of my reaction. Okay. You will have thermometers, but our question is, in general, what does the temperature do to the rate? So you don't need you don't need to be super specific. Does that make sense? So if I heat it up, what happens? If I cool it down, what happens? Okay. All right. So if we're testing particle size, though, I have the same amount, and I've broken it up, and then I would take my hydrochloric acid and put some in. This is something that we are measuring rate. So what do you think would be helpful to know? Time, how long it takes. Okay, so that's something that I should tell myself to do in my procedure. Turn on the stopwatch. There are stopwatches in the lab. Okay, so we could take some hydrochloric acid and put it in here. Maybe I should measure the same amount. I don't know if I'm doing that. Okay. So I just put 1 milliliter in there. So I'm going to put 1 milliliter in there. Okay, this is not very good because I didn't measure the time. I also added different amounts, so that's great. You're going to do this much more carefully, I'm sure. So, okay, I can see there's the vapor coming off is mostly water, but sometimes some hydrochloric acid will also come out. So you need to don't breathe that in. Okay, and we'll also turn our exhaust on. Okay, so I didn't start my timer. I should have done that, but you should be able to measure that. How would I change the concentration? This is another one. This reaction, I could check all 3 things. How could I check the concentration? I have 3 molar hydrochloric acid. Any thoughts?
Use less.
Use less, yeah. Okay, good. Along with that, let me just tell you, let me move this. down. So if I'm changing the concentration, I need to use the same total volume. Because we're using a well plate, it might be a good idea to measure using drops. So like total drops. So total drops should be the same. And then if I'm changing the concentration, so for example, if I do 40 drops of hydrochloric acid, then that's going to be the most concentrated. That will be 3 molar. You don't necessarily have to find the concentration. If I did the total drops, my drops are still going to be 40, but what if I do 30 drops of HCl? I need the same total volume, so I'm going to add distilled water. I would add 10 drops of distilled water. That way my total volume is staying the same and I am changing my concentration. Because if I change the total volume, maybe some of my magnesium isn't going to be covered. Okay, you don't want to be changing 2 things at once. You don't want to change total volume and concentration. Does that make sense? Or if I just drop the number of drops, so if I do 40 drops and 30 drops and don't add water, it's still the same concentration. Okay, I need to dilute back to the total volume. Does that make sense? Okay, so this one would be less concentrated. I could do something like 10 drops of HCl and then add 30 drops of water to get me back to my total volume. Okay, and that way I'm diluting my acid. So this would be a way to change the concentration. So this experiment as a group, or this is in pairs. You're going to do this in pairs. As a pair, so you need to both write your procedure, but you can talk about, do you want to use this experiment to measure particle size, temperature dependence, or concentration? But you need to use one of each of these 3 experiments to measure one of those. 1 per experiment, yes. You have to do all 3 experiments. Each one should measure temperature, concentration, or the other thing, particle size. Okay, so that's the hydrochloric acid and magnesium. Not too bad. The next one, let's do is we'll demo it. I think you've probably all done this before. You have a canister, okay, and we're gonna put in, this is gonna be water, and this tablet, okay. Does it say how much you'll get? Tablets. Okay, it doesn't tell you. So we have a lot of this. The video that I watched said that you need just, like, if you put a quarter in, it'll be a lot. Okay, so for this one, what I would do is I would take a quarter approximately. Maybe you can measure the weight or something. So I would take a quarter for each experiment. And then if I wanted to measure the temperature dependence, so I'm going to add water to this. How much, or what could I do to change the temperature of the water?
Put it in ice.
Put it on ice, or we could heat it up in the tap water. We could use hot water. Okay, so this one would be an easy one to measure the temperature dependence. This one we could also measure the concentration. How could we change the concentration of our tablet? Okay, we can make this smaller. Yes, and then use the same amount of water. Great. So if I make a smaller piece and put the same amount of water, or a bigger piece, same amount of water, that would increase the concentration. Yes, great. We could also add more or less water to the same size particle. So there's a lot of ways to do this experiment. Okay, are you okay?
Oh, yeah.
Oh, okay. I was worried that like this is.
Oh, no.
Did it get over there? Okay. Oh, this one would be another one where we could measure the particle size. How could we change the particle size of this?
Find a similar.
Okay.
Split that one up.
Yes. Okay. So like maybe these are similar in mass, and then maybe this one we could crush using. We have mortar and pestles. You could try that. So this one this would be a good one to measure concentration, temperature, or particle size. So another one that you could pretty much do all of those. Okay. You are deciding. There's a lot of correct answers. And the lab, when I grade this, I'm going to look at your procedure, see what you did, and then look at your results and your conclusion. So this is a lot about explain to me what you found. Explain to me what happened in the lab. Okay. All right. Next lab. Oh, should we do this one? Okay. We'll put some in there. Maybe while this one is going, we'll. Oh, I think this one we're supposed to go outside for too. So if you're doing this one, we will go outside. Okay. Heads up in the front there. Okay, this one. If we need the rate, this one also we should time. Okay, we're measuring how long it takes. I was not paying attention, and that went faster than I was expecting. So, yeah. So another thing you can measure in this experiment is how high that went. Obviously, the ceiling stopped it in here, but we could take it. So the plan would be we go outside right here next to the bricks, and then you can like kind of estimate based on the bricks how high it went. Okay. So. Sure, if you want to use some physics to calculate how high it went, yes, you could time how long it was in the air maybe. Okay. I was not ready for that happening. Great, we got some paper towels. And this is just water and that Alka-Seltzer tablet, so we're good. Yes, all of these can go in the sink. If you have magnesium left over and it's still in the sink, you should fish that out. Okay, we don't want the magnesium to go down the sink. But we're using small amounts of everything, so most everything cannot go down the sink, I think. Okay, last experiment type is you're going to get, this is the cute little Petri dish. I didn't know how big it was when I bought it, so I think this will be fine for this. So what you're going to do is you're going to have an indicator. Okay, yours is going to be in a little vial. And this one is a really small scale experiment. We are going to just drop drops in this Petri dish. So this is like dropwise. So this one doesn't have any particles. This one would be, I would say, probably impossible unless you can think of something else creative. I don't think you can test particle size with this one, because there's not particles. But you could test temperature, and you could test concentration. So remember, you're going to keep the same total drops, just change the amounts, like within the total drops. For concentration, yeah. So this one you could test concentration or temperature. So maybe decide what you're going to test with this one first, because there's only two options. Let's see. So I'm going to put a drop of indicator. This indicator is just going to tell me what's going on. Okay, so right now the indicators are the same color. Maybe, I'm not sure. Is this going to be better to see, or can you see it better this way? Maybe that way? Okay. Okay, so right now I'm going to look at this with my partner, and we're going to decide, okay, they're pretty much the same color. Maybe the inside one looks a little darker because I have a little bit more. And then I'm going to put these two chemicals next to this dot in here, this indicator. And the indicator is going to measure the pH. So the outer one is going to tell me what it started as. And then the green dot in the inside is going to tell me the pH. Okay, this is a universal indicator. It's going to go through a range of colors. Maybe do this one once and kind of see what happens when you do that, when you do the lab. You're going to try to time and see how fast it takes the color to change, okay? You also have to, as a group, decide, okay, what color are we going to look for? Because it's going to, I think it's going to change. What I saw was it's going to change from like a green to like a yellow or an orange color. So you have to decide how much of that color you're going to see before you stop the reaction. Okay, and so each group might be looking for something different. So you kind of have to decide that. What are you going to look for? When are you going to stop the rate? So if I'm measuring concentration, I'm going to change the ratio. If I'm measuring temperature, I'm going to change the temperature of the samples, but keep the same number of drops. So let me see. I'm going to put like, we'll see what happens with 3. 1, 2, 3. Okay, and put that one here. That one was the sulfuric acid. Sulfuric acid is kind of corrosive, so be very careful with that one and the hydrochloric acid, but we're using small amounts, so we should be okay. Even if you spill this, it's not too much. Okay, we're going to put them next to each other. Pretty sure that they go next to each other. Okay, I just put 3 in there. Okay, and then we're gonna see, hopefully our dye isn't old. I have more dye if this one's old. Then we're gonna watch and see if anything happens. And I would start my timer. Does anyone see anything happening yet? Let me see. I can see a little bit of something happening up here. Let's see if we can autofocus. So that's pretty close. Can you see that edge is starting to turn yellow? So maybe my group is, we're gonna stop when the whole outside is yellow. Maybe we're gonna wait till it starts turning orange, okay? But you as a group, or maybe it will all turn yellow, I don't know. So you guys have to decide as a group, when am I gonna start the timer? When am I gonna stop the timer? And then also, I just did 3 of each drop. Are you going to modulate the amount of drops? Like, are you going to say, like, oh, I'm going to do 1 of these drops and 5 of these drops?
That could be for concentration.
That could be for concentration. Or you could change, like, same number of drops every time, but I'm going to put the 2 clear liquids in a hot bath first. And then I'm going to put them at room temperature. And then I'm going to put them in a cold bath and see how the temperature changes the rate. Okay? Does that make sense? Okay, so you guys, there's lots of right answers here, but what you really need to make sure is that you're looking at the 3 reactions, and each reaction is testing something different. One is testing temperature, one is testing concentration, one is testing particle size. This one can't test particle size, so you have to pick one of the other 2 for particle size. Okay, questions for me overall on this lab? Okay, I think let's right now go through the procedure and make sure we know what we are doing. Oh, this one, when you're done with this one, you want to turn the water on and then rinse it down the sink. There's just a small amount here, but you still don't want this to create fumes and go into your eyes, okay? So be careful with that one. All of them, but especially that one. Okay, let's look really quick at the instructions. So first, you need a balanced chemical equation. Well, we have balanced this one before, so you could look at lab 6 for that. Okay, this one is kind of a simplified equation. You can use this as the balanced equation, and this one is also balanced for you. So part of your procedure is writing the balanced chemical equation. Well, most of those are done for you, okay? And you can look at lab 6 for that balanced equation. Okay, and then this is where independent and dependent variables. Do you know what independent variable is? Which one? What you're testing. Good. And what's the dependent variable? What you're measuring. Perfect. That's a great way to say that. Thank you. So you need to think about those things. Okay, I'm going to be looking for those in your procedure. In this experiment, I will be testing what? What are you changing? What are you measuring? Okay. Again, there's a lot of right answers. Okay. And then you're going to come up with a table to record your measurements. And it says, okay, this is a requirement. You need to do at least 3 trials for each thing. So, for example, we did this. Oh, it's starting to turn yellow on the outside. We did this one, that would count as 1. If I heat it up, that would count as 1. If I cool it down, that would count as 1. Okay. If I do particle size, I need at least 3 different particle sizes. If I do concentration, I need at least 3 different concentrations. This packet gives us some ideas on how to set each of these up. So we have our balanced chemical reaction box. The problem would be like, in this experiment, I'm testing temperature. How the temperature affects the rate. That would be our problem that we're investigating. This is what you are thinking will happen. This is your independent variable. I've never seen that before, but IV is going for independent variable. So think about that. Dependent variable. So what are you testing? What are you measuring? Anything that you're going to keep constant. So I'm going to use the same dye every time. If I'm measuring temperature, I'm going to keep the concentration constant. I'm going to have the same person do the drops because I don't want the drops to be different sizes, something like that. Does that make sense? So think through that. And then your procedure. Again, you don't have to use this. This is just like a template. If that's helpful for you, use this. If you don't want to use it, don't use it. And then this would be like your data table. So trial 1, what are you doing? Trial 2, what are you doing? What are your results? Okay, and then graph. So are you graphing temperature versus rate? Are you graphing particle size versus rate? And then conclusions. Okay, and let's see. Before you start, you have to check with me on each procedure. So we'll run through your procedure just like the lab 5. We went through your procedures. And then, okay, I think then you'll have your graph and your results. Okay. Questions for me? As you have questions with your procedure, let me know, and I can either email you or we can talk about it. Okay. All right, let's get the last 3 Alex topics done, and then if we have time, we can work on the lab procedure. Let me throw some of this away. Hey. Yes, hurry back. Okay. Oh, sorry. No, you're good.
I have 5 left. I don't understand this one. I don't understand this one.
Did you try restarting it? Okay. Oh, okay. Sorry. If I have to resolve it, switch the route again. Alex, Dr. 8. We did. Let's check at the end of our topic. I guess I haven't looked at it, but it might be.
We're doing the lab on Friday, right?
We're funny.
Oh. But it's
Then it'll switch the review.
So we need to do the pre-lab before Friday.
Before Friday. Okay. Oh, we can turn those ventilation on. Okay, let me also pull up our topic. I think this is the next one. Using molarity to find solute moles and solute volume. But let's just check really quick. Topic is
You gotta write it.
okay, here we go. Let's just yeah, okay. So when you do the test, there's two of this version of a topic. So there's one of each topic. This topic shows up twice. You'll get two different versions on the test. Okay. So just be ready for that. Again, that means that you'll practice all the topics, and this one you'll have two versions. Okay, so my other class is also talking about this. So this is the three versions of the molarity equation. And that's what we're going to use in this question, this topic. Let me throw some of these away. Get them out of my way. Okay. All right, let me pull up my camera again. I don't need my book. Okay. Should I move my clothes? Whoa. So molarity. Did we talk about this already? Molarity is always moles of the solute over liters of total solution. So moles over liters. If we want to solve for moles, we're just going to multiply the concentration times the volume. So you can write this a few ways. We can say molarity times liters gives us moles. That would be the same as saying concentration. This is what Alex says. Concentration times volume gives us moles. N is moles. We use N for moles. So depending on what we get in the problem is how we will set this up. I put my markers in here. I'm not sure where my markers are. Oh, they're up. Okay, so this would be if we're looking for moles. This is how we would set this up. If we need liters, then we can rearrange either of these. So, for example, if we're looking for liters, volume, we can just divide both sides by concentration. So volume is moles divided by concentration. Oops, I don't know why my box is a triangle. Or volume, which is liters, is moles divided by concentration, which is molarity. So this is, we're just taking our original equation and pre-solving it for the unknown that we want. Okay, question so far? Okay, did they fix it?
Yeah.
Nice. Okay, so let's look at specifically this question. This says, calculate the volume in liters. So this one's going to be mostly about units, following these equations but using the units correctly. Calculate the volume in liters of a 0.0030 millimolar copper 2 fluoride solution that contains 4 moles of copper 2 fluoride. Okay, and this one has 2 sig figs and this one has 3. So we're going to go with smaller sig figs. The answer will have 2 sig figs. This is one that won't tell you how many sig figs. You have to practice recognizing that. Okay, so let me pull this over actually a little bit. So we have, we need, this is in moles. This is in millimolar. So if I need to convert this to molar first. And then our equation says, if I'm looking for volume, I'm going to take the number of moles and divide by the concentration. Okay, so let's do that. Number of moles, which is 4.00 moles of copper, divided by the concentration, which is 0.0030 millimolar. Okay, instead of putting milli, I'm going to put times 10 to the minus 3. And I know that because that's in my Alex data. Oh. And you get the Alex data on the test, so that's nice. So milli is here. Milli is times 10 to the 3. So instead of putting milli, I'm putting times 10 to the 3. Minus 3, excuse me. Question so far? We're doing okay? So then to find volume. So watch what we're doing here with our units. I'm just going to pick up the units and move them down here. So I'm taking moles. I'm dividing by molarity. Molarity is moles per liter. So if I take moles and divide by moles per liter, I flip the bottom and multiply. I lost my, pull out another whiteboard. More paper here. So we'll get moles times liters over moles. Moles will cancel out and we'll get liters. That's what we were looking for. Does that make sense? So if you can keep track of your units, that can help you make sure you're doing the problem correctly. Okay. All right, so let's type in this value. So 4 divided by 0.003 times 10 to the minus 3 milli. Okay, and then I got this number. Oh, that's a really big number. That seems very big. Okay, we're going to type it in. It looks really big though. Okay, I don't know. I'm going to put this in scientific notation. I only have 2 decimal places. Or 2 sig figs.
Mine was that big.
Thought yours was that big too? Okay. Okay, that just seems like a lot of liters. Okay, thank you. Oh, let's just copy paste into there. And then we'll check. Okay. All right, let's do another one. Okay, this one, especially the one in this chapter, I'm going to look at the box to tell me what unit. So for this problem, the 2 we talked about last time, this one's looking for millimoles. Okay, so we have a chemist adds 325 milliliters of a 0.792 molar sodium carbonate solution to a reaction flask. Calculate the millimoles of sodium carbonate the chemist has added. So this one is a little bit different because we're looking for millimoles. Also because we're looking for moles, we're going to use this equation. Concentration times volume equals moles. This is like the same equation, we're just arranging it differently every time. Or 3 ways. Okay, so let's write that down. Concentration, I better not spill that, times volume is moles. Okay, so let's see. We have 0.792 molar, and we have our volume which is, let's write it like this for a minute. Let's think through. 325 milliliters. Okay. So right now, as it's written, this won't cancel out. My units won't cancel out. Okay, but if I look at mole or molarity, this is moles per liter. If I put a little m here and a little m here, that's like putting times 10 to the minus 3 on the top and times 10 to the minus 3 on the bottom. So those will just cancel out. Are we okay with that? Okay, so this is like a shortcut. So if this doesn't make sense, then you'll convert this to liters and then convert it back to millimoles. Because I can replace this molarity with millimoles, I just put moles. Millimoles per milliliter. Milliliters cancels out, and we can just multiply these two numbers together. So that's a shortcut. Let's do the shortcut. Questions so far? Let's better check. Oh, calculator.
So what if the concentration is millimoles per liter?
So that is millimolar.
Okay. Yeah, it's.
So you're saying you have millimoles per liter.
Yeah.
That is the same as millimolar. Oops, millimolar.
Okay. So.
Does that help you or not help
Yeah,
you? Okay. 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 Let's check, make sure this is right. Okay, and both of my numbers, I'm going to practice. This one has 4 sig figs. This one has 3. So I am going to go with the lower number. This one's going to have 3 sig figs. 257 decimal place millimoles. Let's check. Make sure we got that. Okay. Questions on this one?
So if that's millimole, or is that what that is?
Yes, this is
Should I
millimole.
times it by milliliter and without having to convert, or do I need
Let's
to
see.
convert?
You're trying to find volume or moles? Moles.
But it's like the.
Let's see if one comes up like that, and if not, we'll do yours.
It's not that one.
So this one's even different here. So let's do yours first, and then we'll come back to this one. So tell us what you have, Ian.
So 470 milliliters. 2.13 times 10 to the negative 5 of millimoles per liter.
And what they want you to find moles, just moles.
Micromoles.
Micromoles.
So is that what that is? The upside down?
Yes.
Okay.
U is micro.
Yeah.
Okay, this one you might be okay because micromoles and millimoles are like times 10 to the 3 away from each other. Let's see. Let's think through. Okay, so we need micromoles. Let me put this over here. Let's first, yeah, okay. So this is what I'm thinking. So if we take 470 milliliters and we multiply, okay, we're just going to multiply these two numbers together. But we need the milliliters to cancel. This is not good enough. So how can we make this have milliliters at the bottom? Do you remember what we did in the last one? So when we had molar.
An M in front of.
In front of both of them, right?
Yeah.
Yeah, so what if we do that? We put a milli here. And what if we put...
Can you put another M right there?
We kind of can. What we're going to do is, this is already milli. I'm trying to think how to do this. I think we can do times 10 to the minus 3, and now it's micro.
Okay.
Does that make sense? We moved our decimal 3 to the left. Now this is micromoles.
Okay. Yeah. So I would just do.
So then if we multiply those together, yeah, see if that works for you. I think.
Times it by 10 to negative 3.
Yep, so you'll do 2.13 times 10 to the minus 5 times 10 to the minus 3, or if we add those exponents, it's times 10 to the minus 8. And then our milliliters cancels out, and we'll get micromole, and that's what they're asking for. The other option would be to convert this one back to, it was wrong. Okay, so the other option is you're going to convert this to let's just convert this to liters. And now liters cancels out. Our answer will be in millimoles. And then we can convert that to micromoles. So multiply that. You'll get millimoles. And then move the decimal 1, 2, 3 to the left. Or times 10 to the minus 3 for micromoles.
So I'll get whatever I get from here, and then I times that answer by.
Divide by 1,000. Move the decimal to the left 3 times.
Divide what by 1,000?
Your answer.
Oh, so I get that answer and then I just divide by 1,000?
Yes. Because micromoles is 1,000 times smaller than millimoles. Okay. Let's try this one. So we have 385 milliliters of this solution. Calculate the millimoles. Okay, so let's try. Did that work?
No, that was wrong.
That was wrong too?
Yeah.
Okay. Okay, I'll come over and we'll look at it. We'll figure it out. Okay, this one we're looking at 385 milliliters. And we have this concentration. And we're looking for millimoles.
You only really ever divide with liters. Right.
For this problem, yes.
Yeah.
Yes. The other problems are looking for concentration, yeah. But yes, for this problem, yes. Okay, so we're going to multiply again. So this one's liters, this one's milliliters. So let's convert this one to liters. 1, 2, 3. 0.385 liters. This one is micromoles. I'm going to convert that just to moles. Times 10 to the minus 6 moles.
It's minus 6 and then it was minus 3.
Micro is times 10 to the minus 6. Milli is times 10 to the minus 3. So I'm going to divide this by liters. Oh, that's the unit. Micromoles per liter. So liters cancels out. We'll end up, our answer will be in moles. And then, we should have times by 1,000, not divided, because there's 1,000 micromoles per milliliter. I think that's. Okay, so we're going to do 0.385 times by this value, 0.0053 times 10 to the minus 6. This is the value in moles. Okay. There is 1,000 millimoles for 1 mole. This is moles. Yep. So we're going to times by 1,000. So we're going to multiply by 1,000 to get millimoles. And then let's check sig figs. This has 2, this has 4. We're going to go with 2. That's the least sig figs for multiplication and division. Copy this number into my box. Make sure I only have 2 sig figs. Oops. Okay, I'll check. Okay. All right, so this one you have to be familiar with those units. That's something that tricks me. So practice that. Okay, let's see. Next topic is dilution. We got 2 left. Dilution is another calculation question. We just have calculations left. This one we're going to take we're going to use this equation. This is our dilution equation. Dilution is like a ratio problem, okay? So what we do in dilution is we take a sample. So like imagine we have something that's really concentrated, and we're going to take some of that. So imagine you're taking a pipette, you're going to put some in a second beaker, and you add more liquid, more solvent, and you dilute the sample. So what you're really doing is you're saying the moles I took out of the first sample has to equal the moles I put into the second sample. So moles that I took out of the first sample has to equal the second sample. And so what you're going to do is you're going to find the concentration of the first sample, multiply that by the volume that you took out. So maybe you took 1 milliliter out of the concentrated sample, and you put it in a new container. So you put your 1 milliliter and you're going to dilute it to a new volume, and you're going to multiply that by the new concentration. So we know that molarity times volume gives you, this together gives you moles. Okay, I guess this way. So this is just a ratio between the moles that you started with. That is the number of moles that you end with. Does that make sense? Okay, all right. So these problems, there's kind of a shortcut. So what you're going to end up doing is you're going to multiply 2 that are talking about the same solution and then divide by the other number. So read through this with me and let's see if we can figure out which 2 go together, and we're going to multiply. So this says a chemist makes 50 milliliters of calcium bromide working solution by adding distilled water to 20 milliliters of a 6.90 molar stock solution of calcium bromide in water. So these 2 are talking about the same solution. If you find of, that's almost always an indication that you can multiply those 2 numbers. So this one and this one are going to multiply. So I'm just going to find of and multiply, and then find my other number and divide. I also need to be really careful at units on this question. So this one shouldn't be too tricky if you have practiced it a few times. So let's see. We found the 2 numbers that go together are these 2. Oh, let's just put it in our calculator. Oh, we got to check units. We'll put it in our calculator and then we'll check our units. This one times this one. Divide by, oops, we want to divide the whole thing by 50. Okay, all 3 of these numbers have 3 sig figs, so I'm going to put 3. 2.76. Okay, before we push enter, let's check our units. This is another one where we can follow along with our units. Oops, we do need that actually. But like smaller, how do I get it to fit where I want it? There you go. Okay, so we've got 20 milliliters and 6.9 moles per liter, and we multiplied those. So 20 times, oops, I really want the units. Milliliters times 6.9 moles per liter. And then we divided these two numbers by 50 milliliters. So my milliliters are on the bottom, my milliliters are on the top. Moles per liter is the unit that we get to keep, and that's what's in the box. So I don't have to do any conversions. Does that make sense? Okay. All right, so watch out for units. Let's do another one of these. All right. A chemist must prepare 100 milliliters of 135 millimolar aqueous from barium perchlorate working solution. He'll do this by pouring out some of the 0.441 molar aqueous barium chlorate stock solution into a graduated cylinder and diluting it with distilled water. Calculate the volume in milliliters. Okay, so notice there's an of right here. So if there's an of, I'm going to multiply. I'm just going to change that automatically to a multiply. 100 milliliters times 135 divide by this other number. Okay, and this one looks like our units don't match, so we've got to be more careful here. So I'm going to do 100 milliliters times by 135 millimolar divide by this other number floating around. Okay, so I need milliliters. Can you see how these numbers aren't going to cancel out the units? So I need to change this. Well, I could change either one. I'm going to change this one. Instead of writing milli, I know milli is times 10 to the minus 3. And that way, molarity will cancel out. And then I'll end up with the unit that it's asking for, milliliters. Okay, let's type it in.
So the lower hand is always times 10 to the negative 3?
Yes, you can replace that always, yes. As long as you're just directly replacing it. Divided by 0.441. 30.6. Okay, oh, let's check. These all have 3, so my answer has 3. Okay, great. Okay, questions for me on that one. That one's another, just you got to be familiar with units. I am surprised at how many people miss this one, because if you follow that pattern, you just multiply the two numbers that are separated by of and divide by the other one, then it should be pretty straightforward. So especially if you don't have to do any conversions on your problem. When people miss this, they just have no idea how to do it. So this one should be one of the easier ones, I think, because you're just finding the numbers, multiplying them, and then you might have a few units to watch out for. But okay, I'm just always surprised at how many people miss this one. Okay, questions for me on this one? Okay. All right, we have one more. We will see if we can get, we'll talk about the process of this one. We might be able to get through one. This last one is kind of tricky. But let's go through the process and then we will we'll try to do the math. Okay, so let's go here for a minute. So the basis of this is that when we add anything to water, the boiling point increases and the freezing point decreases. So pure water boils at 100 Celsius. You knew that, hopefully. And it freezes at 0 degrees Celsius. Okay. So if we imagine a graph, I'm just going to do a super basic graph where we have our freezing point or boiling. Let's put boiling up here. So this would be 100 and 0. So if we add any solute, so that's just salt or It could be a liquid. If anything we add to water will increase the boiling point. Okay. So like we'll call this like impure. Impure water, the boiling point increases. Or we could call this like a mixture. Mixture. Or we're in the solutions chapter, we're talking about solution. If we add something to the solution, it decreases the freezing point. So I just wrote freezing point. So if it'll decrease the freezing point if it's a mixture. So if we add something like salt. And that's why we salt the roads, because the mixture of water and salt freezes at a lower temperature. Sugar, okay, etc. Okay, so this is where we have to recognize an acid. So how this affects, we have to predict based on mass and number of particles. So if it's ionic or an acid, then more particles affects the temperature more. The boiling point or the freezing point more. So for example, if I have sodium chloride or if I have calcium chloride has 3 different particles it splits into. It splits into calcium, chlorine, and chlorine. Sodium chloride just splits into calcium and chlorine. So this is going to have a greater effect because it has more particles. Okay, so we have to recognize that. This is also where acids come into play. So if I see something like this, I need to recognize this will give me 2 particles. Okay. All right, so we're going to calculate something called the molality for this problem. So let's go here. Okay, also, before you do this problem, you should always get one box right. The box you should always get right is water. The freezing point of water is always going to be the highest. The boiling point of water is always going to be the lowest. Before you start this, always put that in, okay? You're going to get at least a quarter of a point. And then you can figure out this math stuff. All right, next part is we're going to calculate the molality. And we're going to compare the molality. So the bigger the molality, so that means how many moles per kilogram of solution, the larger that value, the more effect it's going to have. Okay? So let's see if we can get through one today. This is a little bit tricky. So the first one we have 9.7 grams of sodium acetate. And it gives us the formula. So looking at that formula, is this going to split into particles? Is this going to be ionic, covalent? Is it an acid? So this one, I see sodium and I see that that's an ionic compound. So I'm going to get something like, let's pull up this. This is going to give me, oh, and it's in 100 milliliters of water. This is going to give me 2 particles. I'm going to get sodium and I'm going to get acetate. So just keep that in mind. Okay, so the first thing that we have to do is we need to figure out how many moles. What we're calculating is molality is moles of particles per kilogram of solution. So the first thing we have to do is calculate how many moles of particles. Well, we have this many grams. So we're going to calculate moles of this. So first thing we need to do is divide by the molar mass. Okay, divide by the molar mass. Sometimes the ALEKS calculator will have the molar mass for me. This is, I don't know why they do this, but in this little, is it this one? Yeah. They have 2 of them, and we have to calculate the other one, so that's kind of dumb. And this one we don't have, so we're going to have to calculate it. So, okay, let's do this for today. We're going to just Google it. You can't do that on the test, but you can do that on your homework. Okay, so we're looking for molar mass of sodium acetate. Okay, great. So we've got this number. 82.03. Okay, I'm just going to write that on my whiteboard. Something like this. Grams per mole. Okay. Well, that will give me moles of sodium acetate. Well, I need moles of particles. And we know for 1 mole of sodium acetate, we're going to get out 2 particles. So I just need to multiply this by number of particles. So this is 2. Okay, so far so good. The next thing we have to, I'm going to get this number because I have sodium and acetate. 2 particles. 1, 2. If I had 2 acetates, it would be 3 particles. Okay. The other thing I need to do is figure out how many kilograms of water this is. So it told me that water has a density of 1 gram per 1 gram per milliliter. So this is going to give me 100 grams. And then to get to kilograms, I'm going to divide by 1,000. So 0.1 gram. And I only have to, kilograms. I only have to do that 1 time. The bottom number is going to be the same for all of them. So if you're really paying attention, you don't really have to divide by that number every time. You can just, you can just look at the largest top number because you're going to divide by the same number every time. Did someone in our class take the hall pass? Is it, sometimes I scoot it to the back. Is it, it's not in the garbage?
No.
Okay, just go, hurry back.
Sure.
Okay, so let's go ahead and plug this into our Alex calculator. Where did Alex go? So this is our process. So we're going to take our number, 9.7, divide by the molar mass, which was 82.03. Then we're going to times this number by the number of particles. And then we're going to take this number and divide by the kilograms of solution. So then I'm going to write this number down somewhere. Okay, so for sodium acetate, my value was 2. It doesn't really matter how many. We're not going to report this number, so it doesn't really matter how many sig figs. So I'm going to write 2.36 just in case I need extra. Okay, the next one we're going to do the same thing, but I already have the molar mass in my calculator, and I already have the kilograms of solution. So we're going to take the next one. So 9.7 divided by, oops, I need to push divide by. Divide by this number. Let's see, this one is glucose. Okay, glucose is covalent. It's not an acid. There's not an H at the front, so it's not going to break into ions. So this one only has 1 particle. So I'm going to multiply by 1, which is going to do nothing. So I'm not going to do that. And then I'm going to divide by the kilograms of solution, which is 0.1. Okay, so this is 0. Was my kilograms of solution 0.1? I erased it. Yeah, that's right. Okay. So this one is sodium. The next one is glucose. Okay, glucose was 0.538. And then the last one is ethylene glycol. So I'm going to do the same thing. So 9.7. Hopefully I put that in right. Did I put 9.7 last time? Yeah, okay. 9.7 divided by ethylene glycol's molar mass, which is this one. Then we're gonna multiply by the number of particles, which is also 1. Ethylene glycol is covalent. It won't break apart in solution. It's not an acid. It's not ionic. Then this number, we're going to take this and divide by 0.1. And this gives us 1.56. Okay, so then I'm going to rank these based on the value that I got. So for sodium acetate, we got 2.3. That's the biggest value. That's going to have the biggest effect. So that's going to decrease the freezing point the most. Okay, do the opposite. It's going to increase the boiling point the most. Does that make sense? So the biggest number is going to have the biggest effect. The second number is ethylene glycol. It's going to have the second greatest effect. And it's going to be the third lowest boiling point. So I'm just ranking them based on my little chart thing. And then and then the glucose has the smallest effect. So it's going to change the freezing point the least. It's going to change the boiling point the least. So we're just going to increase the boiling point just a little bit. We're going to decrease the freezing point just a little bit. Okay, let's better check this one. Okay, does that make sense? So this is the process. Hopefully after the lab, we'll have more time to go over more of these. This one's quite involved, but that's the process. Especially watch out for ionic compounds that give you more particles. So I've seen 2 or 3 that you have to multiply that number by. And especially watch out for acids because we haven't seen those very often. Remember that sheet, you can reference that. It will also say, it gives you the name. So if it says acid, look at it and see if it will split into H and then what ions it's going to split into. Okay.